these slides were a test question I had once, which was, I gave you this code, and you were to have to tell me where it's wrong. All right? And quite frankly, what's funny about this code is that I designed it so that it was wrong everywhere, right? And the amusing thing is that it's actually, the code actually works, right? I made it, sometimes two wrongs makes a right. And so it accidentally it works. All right, so here, right, do we have our loop, a precondition, right? Our precondition is we have an integer, and the postcondition is we've summed up those integers up to capital I, right? Everybody get what the problem is? And then, so some people say on the test, they said, well, what was wrong with this is the precondition doesn't say that I has to be positive, and I might say, well, if I is negative, is this well defined? And I would say it is kind of well defined, and it gives the right answer, so I'm not so upset. All right? People might say, some people complain that I haven't documented my variables. Right? Clearly they took a different course because they're saying you should document your variables. Have I documented my variables? I say right in here they're documented. Right? What's the loop invariant saying? The loop invariant is saying, well, we got some I, we got some S, and they had this relationship between them. Right? So I think I have defined my variables. Right? Alright, so here, anybody see a mistake? What's a mistake in my loop invariant?
I think J is equal to 1.
I equaling 1 to, yeah, J equals 1, we're adding up.
Okay,
What's bad about this?
it always starts at...
Hey guys, you're all going to fail.
The i's are different?
Yeah. Yeah, but that's my loop invariant, is that I don't have the full answer yet. What? No, I'm not missing something. I got too much. No. Action! Who said that? You. He's our man. Each iteration adds the next term. Is that a picture? No, that's an action. So I'm not saying you can't put in here comments, hey, what this action is going to do is to add the next term. I'm saying, don't tell me it's a loop invariant. Right? So here we go. Is that a loop invariant? No, it's an action. Right? So we get rid of that. Now, is this a loop invariant?
Yeah.
Yeah, that's a really good loop invariant. It tells me the relationship between little I and little s. Right? All right. Fine relationship. All right, so now, are we maintaining our loop invariant?
Yeah.
Are we?
Yeah.
This says we've summed up to I. This is kind of the mistake I was almost making before. It says we're summing up to I, and now we're adding I in. Right? So is that right? No, we got I. We're adding an I twice. Right? Everybody see that we're doing it wrong?
No.
You don't see it? Here, S, by the loop invariant, we've summed up to I. And what is our action? We're adding an I. So I gets put in there twice. And that's why the code works, but it's not maintaining this loop invariant, right? If we fly in and we see that this loop invariant's true, in fact, to make this all work, the way to fix it is to change the loop invariant to here to be an I minus 1, and then everything will work, right? But here, we're not going from this to this.
Professor, what if you did I equals to I plus 1 before you did...
Yeah, that would fix it.
Okay.
Right? That would fix it. Absolutely it would fix it. But you see it's wrong, right? The point is that it's wrong, right? So this is just saying, let these be the values before, right? We're at the top of the loop, and these when we come around again, right? And so here we're saying that the loop invariant here tells me this relationship, right? The code gives me this relationship, right? And then together we get this, right? And this is wrong because the I prime's here and the I prime's here. Does this make sense to people?
Yeah.
And we're actually, I probably should move these because we're going to do another example, a slower example about this in a minute. Right? You're adding it twice, so it's no good. Right? How are we maintaining the loop? Are we establishing the loop invariant? Right? Here we set s equals to 0 and I equals to 1. Right? Here, if we sum from j equals 1 to I equals 1, the answer should be 1. Right? The answer shouldn't be 0. Right? Yeah? You guys with me here? What does this say? Well, I equals 1, then the sum should be 1. Right? Exit condition. Here I'm exiting. When am I exiting?
I is greater than I.
When I is greater than I. Right? And if I is greater than I, right? I like exit when better because it helps me better. Right? So here we're saying the loop invariant tells me that. The exit condition tells me little I is bigger. And so together we've done it wrong. Right? Does that make sense? You see here, these are, I always like to give examples of wrong things and right things so that you can better differentiate. If all I give you is right things, then it's harder to know what's right.
So in the loop invariant, didn't you say that we cannot have an action in it?
Yeah?
But isn't s equals to, isn't that an action that we keep on adding?
This?
Yes.
No, this is a math statement. It tells you the relationship between I and S. There's no action here. Right? This is the action. Right? This is a picture. So, you know, follow this. Right? This felt like an action. Right? Now, you might say that this is an action because there's a sum in there. But it's, I'm not telling you to do the sum. I'm saying that the sum is true. Right? If you were to test this, then you would have to do some actions to test it. But as a statement, it's just a statement. Yeah?
Why is the sentence before that statement have to be crossed out?
This one?
Yeah, that's an action.
Because it's an action.
But the bottom one is that too.
Well, that's this one?
Equal to s plus I.
This.
Yeah.
Yeah. This is an action, and we want the code to be an action. We don't want the loop invariant to be an action. We want loop invariant to be a picture. Right? And then what do we want to prove? We want to say, if this picture is true, and you do this action, then this picture will be true again. Right? Does that make sense? Picture, action. Action makes the picture stay true. Yeah?
Can you go over how you said I is getting added twice?
Yeah. Just from the loop invariant, what's the last number that's being added is I. What are we adding next? We're adding I again. So that's a mistake. Right? Because everybody should only be added once.
So progress is bottom line is one of them.
Progress would probably be my value of little I. I mean, the nice thing about little I is I know where it starts, I know where it goes, right? Capital S, well, it starts at 0, but I don't really know its end value. I wouldn't know when to do an exit condition, right? On here, I want to exit when little I equals big I, right? So the advantage of little I being a measure of progress is I know it starts at 0, 1, I knew it ends at capital I.
Does it matter if the exit conditions before or after the loop invariant?
No, I think I might not be so consistent on that.
So it doesn't matter.
It doesn't matter.
Okay, sure.
Yeah. I think generally these days I put it before because I want to emphasize that it's fact, that it's true even when you're exiting, right? So I like it better up there, but on this day I put it in the wrong place. Good question. In fact, we could add that too. And the loop invariant should be before it. And actually, I think I can tell you why I put it here. Right? I put it here because somehow exit when I can put after, but whiles somehow have to be before. I mean, if this is a while, then where else can I put it? Right? If I do loop invariant, exit when, that's the order I like. But as soon as you say while, not exit, then I want the loop invariant to be in here. Right? So I think that's why I have it here. Yeah?
Is the loop invariant established properly at the beginning of the loop?
No, we said that too.
But we haven't fixed it.
We didn't fix anything. We just went through and gave the mistakes. Right? I think somewhere we say, all right. Anyway, here we're saying, and actually the code works. All right, everybody good with that?